Our lesson today is going to be able to solve exponential equations. Exponential equations are equations in which the variable expression occur as exponents. We have some properties of equality for exponential equations. Two powers with the same positive base, where b does not equal 1, are equal if, and only if, their exponents are equal. If 2 to the x is equal to 2 to the fifth, then x equals 5. If x equals 5, then 2 to the x is 2 to the fifth. Alright, so let's look at some examples here. Okay, our first example, we have 3 to the x plus 1 is equal to 3 to the fifth power. So because the exponents, or because the bases are the same, we can write the following equation. X plus 1 is going to be equal to 5. We solve that equation by subtracting 1 from both sides, and we'll end up with x is equal to 4. You know, you'd want to check your equation, right? Make sure that the solution makes sense. If we replace x with 4, is 3 to the fifth the same as 3 to the fifth, right? Because 3 to the 4 plus 1 is 3 to the fifth. So the answer here is yes, right? And that's what we want to work on. So we're going to look at example B. Once again, we see the bases are the same and the equations are equal. We'd have to understand, though, that this 6 has an exponent of 1. So when we write our equation, we'd write 1 is equal to 2x minus 3, right? Because the bases are the same. The exponents are also equal to each other. We solve this equation by adding 3 to both sides of that equation. We get 4 is going to be equal to 2x. We solve this equation by dividing by 2 on both sides of the equation. We get 2 is going to be equal to x. Once again, we check that equation. Right? Check that solution. So if I replace x with 2, 2 times 2 is 4. 4 minus 3 equals 1. Right? 6 to the first is equal to 6 to the first. Our next example here. Once again, we see the bases are the same. So we could write 3x is equal to 2x plus 3. We write an equation that says the exponents are the same. We solve this equation. We see the variables on both sides of the equation. We remove the variable with the smaller coefficient. 3x minus 2x is 1x. Right? These are opposites. That's going to be equal to 3. Once again, I check that answer. 10 to the 3 times 3 is 10 to the 9th. 10 to the 2 times 3 is 6, plus 3 is 10 to the 9th. Alright? You guys can go ahead and solve these examples down here. Alright, if you want to do A, B, and C, right, they're pretty simple. Okay, we'll do A together. Well, example A, we have x plus 3 equals 9. Subtract 3, subtract 3. X is going to be equal to 6, right? Look at the problem B. Remember, this has an exponent of 1. So problem B, we'd have 1 is equal to 3x minus 2. Add 2. Add 2. 3 is equal to 3 times x. When we divide by 3 and divide by 3, they cancel. We get x is equal to 1. We check that answer. 3 times 1 is 3, minus 2 is 1, right? So that works. Problem C, we'll do that here. All right, problem C. 3x minus 4 equals 2x plus 1. Subtract 2x. Subtract 2x. X minus 4 equals 1. Add 4. Add 4. Right, we wind up with x is going to be equal to 5. Alright, you guys can try problems 1, 2, and 3 on your own. Alright, because of time, I won't go through those problems, but and you guys can work on that. All right. Let's go on to, well, let's look at this example down here. Which equation does not belong with the other three? All right. Here we see, right, bases are the same, bases are the same, bases are the same. Right here, right, not. Right, so that one does not belong. Next page. Solving exponential equations where the bases are not alike. To solve some exponential equations, you can first rewrite each side of the equation using the same base. Right, so what does that mean? Well, if we look at example A, 5 to the x is equal to 125. Well, another way of writing 125 is 5 to the third power, because 5 times 5 times 5 is 125. So we can rewrite the equation like this. 5 to the x is equal to 5 to the third. Now we have an equation where the bases are the same. So we know that x is going to be equal to 3. And if you replace x with 3, you'd see that that equation is true. Right? What about example B? Right. Well, when I see example B, once again, the bases are not the same. So we'd have to rewrite this 4 with a base of 2. We know that 4 is the same as 2 squared. So we have 2 squared to the x is equal to 2 to the x minus 3. Well, when we're raising a power to a power, we multiply those exponents. So 2 times x is 2x. So now we have 2 to the 2x and be equal to 2 to the x minus 3. Now we can put the exponents equal to each other. 2x minus 3 is equal to 2x. Oh, my bad. Let's redo that. Right, we get 2x is equal to x minus 3. We subtract x, and we get 1x is equal to negative 3. Alright, and let's look at example C. Example C, once again, the bases aren't the same, so we'd have to rewrite the equations with the same base. I can't write 27 with a base of 9, so we have to go all the way down to a base of 3. So this first example here, 9 is the same as 3 squared. So this is 3 squared to the x plus 2. 27 is 3 times 3 is 9 times 3 is 27. So that's 3 cubed raised to the x power. Then I have to multiply. When we raise a power to a power, I have to multiply. So that becomes, let's see, 2 times x plus 2, right? Remember that. 2 times x plus 2 is going to be, right, 2 times x plus 2, that's going to be 2 times x is 2x, so that's 2x plus 4 equals 3x. Subtract 2x, subtract 2x, we wind up with 4, going to be equal to x. Alright, now let's check that, right? Because I want to make sure that that's correct. So 9 to the 4 plus 2 is going to be 9 to the 6th power, right? Is that the same as 27 to the 4th? Right, so I'm going to use my calculator. Right, I'm going to check that. All right, and let's do 9 to the 6th power. All right, 9 to the 6th power, x to the y is 6, equals 531,441. 27 x to the y 4 equals 531,444. So that is correct. Right? The key there, though, is when we have this x plus 2 power and we raise, when we multiply 2 times x plus 2, we got to make sure that we use the distributive property, right, and multiply that correctly. All right. So we have some examples you can try on your own. Let's do, I don't know, what looks interesting here. Let's see, what do we have here? All right, let's do, I don't know if I want to do all of them. All right, let's look at these fraction ones down here. That looks interesting. All right, in the notes, the other problems are done, but let's look at these fraction problems. Let's do some of these. So we have 1/2 to the x is equal to 4. So we have to write 4 with a base of 1/2. So how do I write 4 with a base of 1/2? Means the exponent's going to be negative, right? So that's going to look like this. Oops. I don't know why that just moved, but it did. All right, so let's put that back here. All right, so let's write 1/2 with a base of 1. Write 4 with a base of 1/2. So we're going to have 1/2 to the x. That's going to be equal to 1/2 to the negative 2, because 1/2 to the negative 2 is the same as 4. So now we get x is going to be equal to negative 2. All right, this next one here, same idea. Can we write 64? Can I write 64 with a base of 4? 4 times 4 is 16, times 4 is 64, so yes we can. All right, so this is going to be 4 to the x plus 1 is equal to, now how do I write 1/64 with a base of 4? Well, that's going to be 4 to the negative 3. All right, so we have bases are the same. I make my exponents equal to each other. X plus 1 equals negative 3. Subtract 1. Get x is going to be equal to negative 4. All right. I continue. Some other examples. Let's click to the next page. Trying to do that. I'm using my travel computer, which does not work as well as my computer at home. All right, let's see. Trying to go to the next page, and it doesn't want me to go to the next page. All right. Eventually it will. Okay. Computer's bugging out here. Let's see if I can get this thing to stop. Oh, there we go. And next page. Alright, so these are some problems you guys could try on your own. Writing some of these with the same base. Let's see, anything look interesting? A and B are pretty much the same as what we did down there. Let's see. This one's interesting. Let's do problem 7 and 8. Look kind of interesting. So problem 7, we have to rewrite the 9 for the base of 3. So 9 we know is 3 to the second power. We're raising that to 2x. And then we have, that's equal to 3 to the x minus 6. When we raise a power to a power, we have to multiply those exponents. So 2 times 3x, 3 squared, 2 times 2x should be 4x. So that's going to be, that's going to be 4x, right? 2 times 2x is 4x. It's going to be equal to x minus 6. Computer's going crazy. Let's do that again. Right, so we have, do that again. 9 is the same as 3 squared, so we have 3 squared to the 2x. That's equal to 3 to the x minus 6. 2 times 2x is 4x. So we have 3 to the 4x is going to be equal to 3 to the x minus 6. Now we have bases that are the same, so we have 4x equals x minus 6. We subtract x, end up with 3x equals negative 6, divide by 3, and we wind up with x is negative 2. All right, and we have to do kind of the same thing here, but here we'd have to use the distributive property for this next one, because we can't write 8 with a base of 4. So this 4 we have to write with a base of 2. So that's 2 squared to the 3x. And this 8 we have to write with a base of 2. So that's 2 times 2 times 2. So that's equal to 2 to the third power. And that is to the x plus 1. When I raise power to a power, I have to multiply these exponents. So 2 times 3x is 6x. So we have 2 to the 6x. That's equal to, here I have to multiply the 3 times x plus 1. So that's going to be 2 to the 3 times x plus 1, which is going to be 3x plus 3. Now we've written this equation with the same base, so I can make the exponents equal to each other. 6x is equal to 3x plus 3. Subtract 3x, wind up with 3x is equal to 3, divide by 3, and get x is going to be equal to 1. Right, and you could still check your answer with a calculator, so let's check this one because it was a little complicated. So we have 4 to the 3 times 1, right? 4 to the 3 times 1, so that's 4 to the third. Here we have 8 to the 1 plus 1, so that's 8 to the second power. 8 to the second power we know is 64. We know 4 to the third power is 64, right? So they're equal to each other. So you can check these answers when you get answers and make sure they're true. All right, let's go to our next page. We can solve exponential equations by graphing as well. Sometimes it's difficult or impossible to rewrite each side of an exponential equation using the same base. You can solve these types of equations by graphing each side and finding the point or points of intersection. Exponential equation could have no solution, excuse me, or they could have no solution, one solution, or more than one solution. All right, let's take a look at some examples for each here. All right, this first example, we have 2.4 to the x minus 1 equals 5.76. And like we said, this is impossible to write the bases the same. So we're going to graph each of these two equations. So this first equation, we're going to write graph by making an xy chart. Oops. So we have x and y. All right, and if we replace, we'll go with -2, -1, 0, 1, and 2, and we'll see if we need any more. So when we replace 2.4 with -2, -2 minus 1 is -3. What is 2.4 to the -3 power? That's 0.072. 2.4 to the -1 minus 1. That's 2.4 to the -2 power. That is 0.17. 2 to the 0 minus 2.4 to the 0 minus 1 is 2.4 to the -1. That's 0.42. This is going to be 2.4 to the 1 minus 1 is 2.4 to the 0 power. And everything to the 0 power is 1. 2.4 to the 2 minus 1 is 2.4 to the 1, so that's 2.4. And let's do one more. So that's going to be equal to 3 minus 1 is 2. 2.4 to the 2.4 to the squared is 5.76. All right. So I think we see our intersection point there, but let's pretend we don't. This other equation, right? This equation here, we're graphing the equation y equals 5.76. Right. So if we're starting here at 0, 1, 2, 3, 4, 5. 5.76 is going to be a horizontal line right somewhere up here, right, intersecting the y-axis at right this point here, which would be 0, 5.76. When we graph the other points here, -2 and 0 point whatever, that's almost right on the line. -1 and right, that's very close. 0 and 0.42, a little less than half. 1, 1 is here. 2 and 2.4, that's close to 2.5. And 5.76 is going to be here. So we see our solution here. Right, our solution is this point here. And that location is at 3 on the x-axis, 5.76 on the y-axis. So there's our solution for the first problem. Right, we have one solution because there's one intersection point. Let's take a look at B. So we're going to graph this equation first because that's the easy one. That's y equals x plus 1. So we're going to put a point here at 1. And we go up 1 over 1, up 1 over 1, up 1 over 1. Right? So we get this line here. That's an easy one to graph. Oops, kind of messed that up. That's a little sloppy there. That's better. Right? So we get that line there. The other line, we have to make an xy table. Xy. And we're going to use -2, -1, 0, 1, and 2 and see if we need any more. -2, -1, 0, 1, and 2. 3 to the -2 minus 2. 3 to the -2 plus 2 is 3 to the 0. Anything to the 0 power is 1. -1 plus 2. -1 plus 2 is 1. 3 to the first power, we know that that's 3. 0 plus 2 is 2. 3 squared is 9. 3 to the 1 plus 3, that's going to be right, and then it starts to get real big, right? Because if I put 1, that's going to be 27, right? So that really doesn't help me. So I'm going to go with a -3 here. Just go in the other direction and see what happens. So if I use -3, -3 plus 2 is -1. That's going to be what? 3 to the 1/3, which is -1 over 3. All right, 3 to the 1/3 is, no, that's positive. So that's 3, that's 1/3. All right, so that's a little better. So let's graph what we have here. We have -2 and 1. Right, where's -2 and 1? That's right here. We have -1 and 3. -1, 3 is up here. 0 and 9, 2, 4, 6, 8. Right, 0 and 9 is all the way up here. Right, 1 and 27 is real high. -3 and 1/3. Right, that's back here. So we see our asymptote. It's going to approach x. Right, it's going to approach 0. So we're looking at this line here. Notice there's no intersection point. So this would be an example of a no solution problem. All right, and let's do one more where we have more than one solution. So let's on the next page. All right, let's problem 11, where we have more than one solution. So first we're going to graph 3x minus c. So we would start all the way down here at -8. Well, let's try this again. All right, we'd start all the way down here at -8. And then, right, we go up 3 over 1, up 3 over 1, up 3 over 1. Let's try to fix this. This is a little sloppy. All right, that's a little better. A little better. And then extend this. All right, got to go down to -8 and put a point. 2, 4, 6, 8. So here's -8. And then we go up 3 over 1. 1, 2, 3. Up 3 over 1. Right, up 3 over 1, and so on, right? I'm going to graph that line. I'm going to have to extend that line too, right? Because we don't know where the intersection point is. So I'll extend that line, a good distance. 4 to the x minus 3, we're going to have to make a graph. So I'm going to go my xy graph, my xy. I'm going to use, well, I don't want to use -2 because -2 minus 3 is -5. 4 to the -5 is going to be something really small. So let's start with, I don't know, 1. Because 4 to the 1 minus 3 is 4 to the -2. 4 to the -2 is 1 over 4 squared, so that's 1 over 16. So that's still a small fraction, but manageable. If I replace x with 2, 2 minus 3 is 1, so it's 1 over 4. So let's use 1, 2, 3, 4, and 5. 3 minus 3 is 0. Anything to the 0 is 1. 4 minus 3 is 1. 4 to the first power is 4. And 5 minus 3 is 2. 4 squared is 16. All right, that should be good enough. We have 1 and 1/16. That's going to be really, really close to, right, the line. 2 and 1/4. That's more like that. 3 and 1, like the deli, is right there. 4 and 4. Oh, we got a point right on the line, it looks like. Then we go 5 and 16. Well, if we go 5 and 16, all right, where's 5? There's 5. 16 is going to be all the way up here somewhere, right? So what we have here is, right, a curve. Oops. Let's try this. It's going to look something like this, and then it's going to go way up here. Right? But you're going to have 2 intersection points. Right? That's what you're going to have here. So you have 2 solutions. You have a point here at what? Right? You have a point at 3 and 1. Oops, I messed up there. That's my bad. Alright, that's my bad. Because 3 and 1 is here. Right, that's where 3 and 1 is. And you have a point at 4 and 4. Right, so here are your solutions, right? And then it goes, not here. My bad, a little sloppy, a lot of. Alright, it's going to go here's 4 and 4, and then it goes up like this. So you have 2 intersection points here at 3 and 1, and you have 4, 4. Right, so that's an example of a problem that would have 2 solutions, right? We have 3 and 1, 4, 4 with the curve, right? And with our line, we see we have a point here and a point here. Right, so those are some of the examples that you would do. I don't have time to graph them all because the video would be too long, but I hope that that's been reasonably helpful.